Alright, this is the next video. This is going to take the coin flipping situation that we know is a binomial random variable, and we're going to use a normal model and see, how close a normal model is to a binomial model. In the previous problem, you computed the mean to be 50 and the standard deviation to be 5. So we're going to use this normal model right here. Okay, now I've written the answers to what we got when we used the binomial model here on the left side. Okay, and actually there's one more that I didn't write. Alright, but now I've done it. So I'm going to go through the first couple, but since they're all similar, they're all just using a normal model, so we need to remember how to find z-scores and so forth. I'm just going to do the first couple, and then I'm going to put all the answers down, and then we're just going to talk about what we should see here. Okay, so with the first one, we're finding that probably x is greater than 59, and we're using a normal model. So this normal model has a mean of 50. So 59 is going to be about right here. And it's a little bit less than 2 standard deviations. Actually, 59 is further. Let me redraw that. So 59 is, somewhere out here. We're going to find this little area right there. Okay? Well, we need to find the z-score. Okay, we're using a normal model here. We know the data aren't normal. We're just using it to see how close it is. So remember that a z-score is the value minus the mean over the standard deviation. We get a z of 1.8. And now we're going to use normal CDF. Okay, now you know the difference between a normal model and a binomial model. Now we've got two cumulative density functions, 2 CDF. Just make sure you pay attention to which one you're using. Okay, I've seen people do an entire test using normal CDF when they should have been using binomial CDF. Okay, and they really didn't know what they were doing. They just made that mistake. So pay attention to what the random variable is that you're doing, and this random variable is, we're saying, is approximately normal here. Okay, so we would go normal CDF 1.8 comma hella big number like 5 or a million, and we get 0.0359. Okay, I'll highlight that in blue. Okay, and we're supposed to compare that to what we got in number 1 on the previous problem, and you can see that they're not exactly the same, but they're not that far off at least. Okay, so we do the same thing for number 2, or for part B. We're now finding between 35, which is way over here, and 59. We find those 2 z-scores, and you're going to get that those z-scores are -3, because it's 3 standard deviations below the mean, and we just found 1.8. So again, I'm going to use normal CDF, and I'm going to go -3, comma 1.8. Okay, and I don't need the hella big number or anything like that. And I get 0.9627. Okay, and again, what I can see is that when I use the binomial model, okay, actually I messed that up. This is not the correct thing we got for the binomial model. The binomial model, we got 0.97066. So when we use the binomial model, we got about 97%. When we use the normal model, we get about 96%. Pretty darn close. Okay? The rest of these, we're going to do the exact same way. We're going to find a z-score, or multiple z-scores, and we're going to use normal CDF to find the probability. So I'm going to stop it now. I'm going to write the answers, and then we're going to do the comparison. All right, so now I have the answers to these using a normal approximation in blue, and the answers using the binomial model in yellow. Now, the answers that are in yellow are the exact answers. The answers in blue are just approximations using a normal model, and we know the data aren't actually normal. Okay, so the question might be, why would we ever do this? Well, we're going to find out soon where it makes it so much easier to do this, and we're not going to be off by that far. So now, I want you to notice the first 2. They're pretty close. 0.028 and 0.036. 2.8%, 3.6%. Those are pretty close. Now, the thing is, remember, the normal model is discrete, or sorry, normal model is continuous. The binomial model is discrete. So under the normal curve, there's actually area between 59 and 60, not including 59 and 60. So when we just do greater than 59, we're sort of missing part of the things that we might count as 59. So part D, I'm saying greater than 59 and a half. This is known as a continuity correction to make our approximation better. Now, we're not really going to mess with this too much in this class. I just wanted to show you how close we could actually get if we make this correction. All right, so here is what we get using a normal model, 0.0287, and here's what we get using a binomial model, 0.02844. Look how close those are. We're awfully darn close. Same thing, when we do a continuity correction to find between 35 and 59, and we do this, we get awfully darn close to, 97.06% and 97.03%. This one is 0.000895. This one's 0.000967. Awfully darn close. So a normal model seems very accurate. And we can make it even more accurate if we do these things called continuity corrections. But again, I don't want you to worry about that. What I want you to see is that there are conditions in which a normal model approximates a binomial model pretty well. We know it's not perfect, but it approximates it pretty well. And that's going to come in handy later. The question may be, when is this true? When is it appropriate to use a normal model to approximate a binomial model? Under what conditions? When will the approximation be pretty good? Okay, we're going to look at that in class, and I'm also putting another video here in this sequence that you can watch on your own if you want to preview why this is true.